You record, yeah? Perfect. So welcome everyone to a new colloquium in the Northwest Database Society in series. Today is my great pleasure to have Luca Scheerer. Luca, he is I would call him a traveling graduate student. He just received his master's from ETH Zurich. But he actually worked at the University of Zurich for almost across the street. And he's now a visiting scientist and visiting student at Stanford. He actually collaborated with a team of people, including some people from here, on a project that was started by Anton Lykov and then continued by Luca, essentially, with collaborators from the RelationalAI and from the University of Zurich. So here we go. So before we start, actually, feel free to ask questions, but please be aware that the talk is recorded. After the end of the talk, we will stop recording, and then you can ask questions without being recorded. Okay, Luca, take it away.
Thank you so much, Dan. Yeah, as Dan mentioned, my name is Luca, and today I'll be presenting our joint work, people here at UW, RelationalAI, and Dan Olteanu from UCH. Our work is titled QirK, Question Answering by Intermediate Representation on Knowledge Graphs. So I'm pretty sure everyone in the room is fairly familiar with the concept of knowledge graphs, but just in case to get everyone on board, a knowledge graph allows us to store data in a more flexible fashion as compared to relational database systems. What we model typically is entities in the real world, and we can describe a relationship between those entities as edges and nodes in this knowledge graph. So for instance, here we have Alan Turing, and we can denote the fact that his country of citizenship is the United Kingdom, or that he was educated at Princeton via the corresponding edges. We can also describe more complicated relationships, such as that he is the main subject of the movie Imitation Game, and that this movie also contains Benedict Cumberbatch in the cast, right? But just describing the data is fairly uninteresting. It gets interesting when we start to actually query the knowledge graphs, right? And the way we do this is we introduce a variable, and then we list a set of constraints on that variable, and then the query result will be the set of satisfying the set of basically entities that satisfy the constraints we impose on the variable. So for instance, if we want to retrieve Alan Turing's country of citizenship, we would introduce the variable country, and then we would basically add constraints to the symbolic variable stating that Alan Turing's country of citizenship is said country. And this would basically query exactly for that edge, which we've described in the knowledge graph, and we would retrieve the correct answer of United Kingdom. And logically, this also lends itself to more complicated questions, such as if we wanted to retrieve movies where they center around Alan Turing, but also star Benedict Cumberbatch, we would once again introduce a variable and then list a set of constraints that need to be satisfied for this variable. So for instance, we could first say that the movie has to include Alan Turing as its main subject, and that it has to have Benedict Cumberbatch as part of the cast, right? And this, in this case, would retrieve the answer of Imitation Game. So I would argue that querying knowledge graphs in general is fairly intuitive, at least on a high level. But in practice, of course, this is substantially more complicated, because what we're doing in reality is not querying for entities using natural language, but we have to know the specific unique identifiers corresponding to the individual entities. And this makes querying knowledge graphs substantially more complicated. And this is kind of worsened by the fact that knowledge graphs might not be as pretty as this one in our example, but there may be inconsistent use of certain predicates, or we may not directly know which entity we want to be referring to. Maybe there are two entities with the name film or movie, and so this really becomes cumbersome to even retrieve the identifiers that we want to query on. And then once we have them, we have to compose them into these queries, which are very difficult to read and or write, right? So while the concept is very easy and intuitive, it's quite complex in practice. On the other hand, we've seen the emergence of LLMs, And they're basically on the complete opposite spectrum. They're extremely easy to query and to use, right? So we can just ask the questions we had before in natural language. So for instance, if we just wanted to get the country's citizenship, we would just pose the natural language question, and then we would get the answer in most cases with appropriate context, right? And so this is, of course, a way more user-friendly approach to question answering. And so even the more complicated question we had before, where we wanted to retrieve movies about Alan Turing and include Benedict Cumberbatch in the cast, also work. And again, here we get some very nice context about the movie, but most importantly, it answers the question correctly. And so this is basically the way we want to interact with question answering systems. But unfortunately, this also falls short, right? So as soon as we start to ask more complicated questions, so for instance, if we ask for people who have received an Oscar for Merit and a Turing Award, just a conjunction of two individual aspects that it can answer, it fails, like most popular LLMs will fail to answer this question. So for instance, ChatGPT just states that there aren't any people who have won both, right? Or we can have Google Bard just say that there is a supposed winner, right? And just it's Steven Spielberg, even though to the best of my knowledge, he has not yet won a Turing Award. So this is of course a problem. And then even Bing Chat, right, that in theory should have access to the entire internet, fails to answer the question. It tried to find some information, but failed to do so, right? So this is a problem. They're user friendly, but the answers are wrong, so not really useful. And so this is basically where QirK comes in. QirK tries to combine the user friendliness of LLMs, but with the complete and accurate results of knowledge graph query. Right. Without further ado, let's get into the architecture of QirK. So like I said before, it all starts with the user in our approach. So we'll have a natural language question as with the LLMs. We'll use this natural language question to generate an intermediate representation. And what this will mean exactly, I'll get to in just a second. We'll be using an LLM to do this task. But notably, this task will, as you can see in just a second, this will be considerably easier than answering the full question, right? And it will not lend itself to hallucinations as much, right? And then once we have the intermediate representation, we'll parse this and stepwise transform this into something that we can actually query on the knowledge graph. So in the first step, we'll transform it into a query graph. And up until this stage, everything has not been very dependent on the concrete knowledge graph that we have. And then we'll introduce another stage, which is the entity property matching that will ground the query graph that we've generated onto concrete entities and properties found in the knowledge graph. Using this information, we'll annotate the query graph into something we call executable query graph. And then from this, we can synthesize the appropriate query on the knowledge graph. Right, and then we have a final stage, which is post-processing, which will take the outputs from the knowledge graph and then transform this into something that the user can interpret even better, and then you can see exactly how their results were retrieved. And then finally, this will be sent to the user as the response. Right, so let's dive into the components in a bit more detail. So like I said, the first stage will be parsing the natural language question. So as with LLMs, our input to the program will be a natural language question. So let's take, for instance, the example that failed earlier. So we will want to find people that have won both an Oscar for Merit and a Turing Award. We'll instruct the LLM to generate a so-called intermediate representation. And this is one of the possible examples, as LLMs are not, the mapping via LLMs will not be deterministic, but this is, for instance, one way this mapping could occur. So this is something that we call the intermediate representation, but on a high level, this represents or strongly resembles first order logic. So just to explain this a bit, we're seeking X such that X satisfies the body of the query. In general, in the head of the query, where we have X currently, we could have multiple variables, but just for simplicity here, we'll just have one X. And then in the body of the query, we'll add constraints as with Sparkle before that need to be satisfied. So in our case, we'd want X to have received an Oscar for merit and X to have received a Turing Award, right? And we'll see in just a second how this basic syntax can be extended to more complicated concepts that we need for effective knowledge graph querying. But this is already the core idea of the knowledge graph. And the key fact here is that nothing needs to be actually present in the knowledge graph. As you can imagine, there's probably not going to be an entity called Oscar for merit in the knowledge graph because it's actually called Academy Award for merit. So this won't probably be an entity within the knowledge graph, and there won't likely be a received award predicate within the knowledge graph. But at this point, this is still fine. This is the intermediate representation will just convey the user's intent in a more structured and logical form than the natural language we had above, right? And just to quickly introduce some more advanced concepts as part of the IR. So for instance, we could have type information. So oftentimes you're not interested in retrieving other nodes as part of the knowledge graph, but you want to retrieve some kind of constant value. So for instance, we may want to retrieve Alan Turing's date of birth. And the way we would do this is using a IR similar to this. So we want to take the node Alan Turing and then retrieve its his date of birth, and then tag this -date suffix to indicate that we're looking for a constant and not a node within the knowledge graph. Oftentimes we want to perform aggregation, and this we can also do fairly easily via the IR syntax. So for instance, here we're interested in the tallest US president, or more precisely the highest height recorded for a US president. So we'd say that X has to be a US president and that X's height is Y. Again, Y has, we annotate that Y should be a numeric value and not a node. Again, here we could strip this numeric suffix because it's automatically inferred by Max, but I've just added it for completeness. We could also add qualifiers, and just to back up a bit more, about what qualifiers are. This is a concept that some knowledge graphs have, and in particular Wikidata has, which is that it's a generalization of edges where we can annotate edges with arbitrary properties. So for instance, we could annotate an edge with its validity. So we could say that Barack Obama is the US president, but not anymore. So it has some validity. So we would give this edge a start and an end date, and that we can use to perform more advanced queries. And the way we express this in the IR is that we retrieve again the edge indicating that Barack Obama is a president. And then we label this edge via this colon equals syntax. So we give the edge a name, and then we can use the edge in the remainder of the query to do further queries as if it were a node within the knowledge graph. So here we first get the edge indicating that Barack Obama is president, and then we get the start time corresponding to this event, and this query would return when Barack Obama became president. Right. And then finally, one thing that may be worth pointing out again here is the inconsistency within the IR, right? So we can use position at the top here to indicate that that someone is the US president. We could use holds position, right? We could use president of the United States. We could just use president. So at this stage, it's very flexible. It's not a very robust syntax. The syntax is robust, but it's not in a very precise or robust form. Then what we're often also interested in when querying graphs are cyclic queries. So for instance, here we're retrieving movies such that the director of the movie is married to a member of the cast. And the way we express this is just as a conjunction of these multiple conjuncts stating an individual fact. So we would say we're looking for movies M, and then the director of M is D, and D is married to an actor, and that actor has played in the movie, right? So we just decompose the query naturally into its individual elements. Right, okay, so with this, we basically covered most of the IR. Now, once we have generated the IR, we want to bring this into a more usable format, and this is where we generate the query graph. So again, taking the query from before, where we're interested in basically actor and director pairs that are married and have contributed to the same movie. The way we map this to a QirK graph is fairly straightforward. So we basically turn everything into nodes. So each individual atom you can see at the top will be transformed into a node. Notably, this also includes any kind of edge labels here. So all of these edges are also the edge labels also correspond to nodes. So each of these edges are actually kind of hyper edges that connect 3 nodes, and the source, the target, and the edge label. Yeah. Yeah.
Right. So like,
oh, yeah. Yeah.
So right, so the user is going to kind of give the question natural language, like
yeah.
the question that you're using as an example. You could ask the LLM directly to generate Sparkle.
Yes.
But if you do that, then there might be like non-existing edges, right? And
yeah, exactly,
so
exactly.
This is the problem.
Yeah.
So instead, you have your own intermediate representation, and you're asking the LLM to generate
the intermediate.
But then it could also be wrong. I mean, it could also generate like
yes.
But because also like what you're proposing here, aggregation, Sparkle has a lot of
yes. So the core problem that we're addressing is that it's very difficult for the LLM to remember these concrete identifiers, right? So it could, in theory, write like the first claim is that our intermediate representation is easier to generate than Sparkle, which is debatable. But the more important point is that it's very difficult for the LLM to basically remember all of the concrete identifiers, right, that we saw in the introduction. So it would need to remember the exact ID of Barack Obama. And if it got that wrong, the entire query would be useless, right? And this makes it more complicated in general. For it to generate concrete Sparkle. And then we have also some mechanisms here to patch the IR in case it generated an invalid IR.
And there's more things that kind of just standard across queries where all the specific identifiers or names are going to be part of the kind of parameters in case.
Yeah, exactly. So yeah. There we'll see exactly how this mapping occurs later on, but it's going to be a more standard approach. Yeah.
If I can add to that, one thing about the syntax that is important to understand is, for example, in the first example, there's actually 2 natural language strings, not 1. Exactly, right? So equally valid would be birthday, equally valid would be born on, right? And the idea is
all of this the LLM might generate.
Yeah.
And then you'll be able to handle.
Yes, exactly. So it has a lot more flexibility to do something wrong in our case, right? So it doesn't need to generate the exact string Alan Turing. It could probably just use Turing or birth date, like Mo said, right? Yeah.
Go ahead. Is there intuition? The identifier thing makes perfect sense. You could imagine using Sparkle, but just allowing it to use natural language identifiers. Is there intuition for why this kind of more data log style language is easier for the LLM as opposed to Sparkle, which you might have seen like a number of examples on?
Yeah. The intuition here is, I mean, that's an equally valid approach, I assume. Here, our intuition is just that this is presumably a bit easier because it resembles first order logic, and you just have to add these together, right?
That makes sense, yeah.
But you could generate Sparkle. My assumption here is that it's a bit more complicated and it makes things a bit more difficult to patch up on the end, but I think it's an equally valid approach. Yeah.
Can you go back to a slide where you show the IDs of the knowledge graph?
Yeah.
Because I think you can solve the problem very differently.
Yes. So
this one, exactly.
Yeah.
You're saying basically you're using a language model to learn that WD whatever Q7 is something like. Why don't we just do a mapping? Because I would never query it in this way. So if you say that Q whatever 750, and because it has a one-to-one correspondence to something more meaningful. So if you do this one-to-one correspondence, you have a natural language expression for this one. You can immediately use it in your natural language. So you don't need a large language model for learn something, which is a trivial one-to-one mapping.
Oh no, maybe there's a slight confusion here. So we're not using a large language model to learn the identifier mapping. this we'll get to in just a second. We're going to use the the LLM just to synthesize the IR. So just to decompose the natural language question into something that we can use later on to match against concrete entities of the knowledge graph.
But I would still reformulate this one because no one will be able to know what WDT P27 is. So what I'm saying, you could even do one more step.
Yeah.
Just saying this, we're just starting with the same knowledge. I think this knowledge graph is how it is done. It's completely unusable.
May I suggest a little anecdote? So when we started this project, I think this was 2 years ago, so several PhDs and on the Zoom meeting were trying desperately to ask any meaningful group query on Wikidata. Where do you start? Because we have no idea how to get these identifiers. We had no idea how to get from the movie title to the identifiers. So you poke around, and the meeting is over, and you still don't have an answer. So that was one of the motivations for this project. No matter how you look at it, it's very hard to write the right Sparkle query. You need some kind of additional tools, and this is what you guys is showing us.
And because DBP is a bit better than
I don't know much, but it's much more. So
but it's more readable.
Yeah, but again, in the optimal case, the user would not even see the generated Sparkle. So we're not trying to make it easier to write Sparkle. We're trying to answer questions in natural language. So we're going to go directly from natural language to the answers.
The other thing is the labels are often in Wikidata not as helpful as you might think. So the entity that has the exact label America is a band from 1917.
But that's why I question whether Wikidata is a good knowledge graph.
It's the biggest knowledge graph we have, and it's what we want to work with, right?
But yeah, maybe we can discount that one because DBP is a much better knowledge graph, even though it's also not too nice. But yeah, we discuss it.
Yeah, that's right.
Okay, what we can also see here, so again, just to catch everyone up, we translate everything in the IR into nodes in the query graph. We can also see is that we will apply rewrite rules for unary properties. So for instance, here, to indicate that M is a movie, we had this neat syntax of saying movie M. But of course, because it's a knowledge graph, we won't have the direct correspondence to a unary predicate. So we'll translate this into the instance of thing we can see here below, where we say we expand this to M instance of movie. And again, movie will be a node within our query graph. And just for completeness sake, aggregates would also be transformed into nodes, and we can just immediately represent any kind of filters or equality constraints as edges between nodes in the graph. Okay, and what is the primary motivation behind doing this? So we want to ensure later on, and we'll see why this is relevant, we want to ensure consistent mapping from nodes within the query graph to actual entities in the knowledge graph. Right. So now we can actually get to the part where we take this intermediate representation and we'll map it onto the knowledge graph. So yeah, as I said before, in the IR or in the query graph, all of the properties or entities that we will be referring to are not actually necessarily part of the KG. If they are, perfect, but most likely they will not be. And so what we do is offline, we'll build a similarity index for all entities and property labels. And then we'll, at query time, perform semantic similarity search to resolve the relevant entities and properties. And then we'll just, because this is again, maybe tying into this, because Wikidata is not a very clean knowledge graph, we have to perform some re-ranking to ensure that our results are good. And what we settle on is incorporating the label descriptions as well as the popularity of a node to re-rank the results. And this improves our accuracy and also the efficiency of the approach. And with this, we can rewrite the query graph we generated earlier into what we call the executable query graph, which is basically essentially the same query graph, but annotated with the retrieved set of identifiers. And we'll see how this plays out in just a second. So again, with our query here looking for directors and cast members that are married and contributed to the same movie, we'll annotate every node with the relevant identifiers. So for instance, we have the node married here, and we'll resolve that to spouse P26 via the similarity index. And similarly, we'll do the same for director, which happens to perfectly map to or a property within the knowledge graph. So this mapping is fairly trivial. Cast gets mapped to cast member. And where it becomes interesting is for movie. So here is what we have. We have quite a bunch of entities that we think could be important here. And this is the kind of flexibility of our approach, that we allow multiple matches in this stage. So for instance, here we will have movie, which is actually the Wikidata disambiguation page, which won't help us a lot. We have the thing we're actually looking for, which is film. So this indicates that something is a movie. We have a music album called film. We have the category B movie, and we have an actual movie, which is called movie. And as you can imagine, all of these have very high similarity scores to what we're trying to retrieve. But at this point, we don't necessarily know which one to use, right? And the key insight by Anton here is that we can resolve this semantic ambiguity directly via the knowledge graph, namely due to the fact that it will only ever be true that a subset of these combinations will actually be semantically meaningful, right? So you would not have necessarily a director of a disambiguation page, right, or of an album. And so this would immediately disqualify one of these matches from appearing in the final result. And so at this stage, it's fine to have more matches than strictly necessary, just to filter them out later to what is essentially semantically meaningful. Right, and so with this, we've basically generated the executable query graph, and we're ready to execute something on the knowledge graph. And the way we do this is we generate some Sparkle code from the query graph. I wrote here that we need about 300 lines of code for this. This is a bit much. The only reason it's this high is that we also need to consider basically these qualifiers and the aggregates. They make up the the majority of this code. So in reality, it's probably like 50 lines of code just to transform the query graph into Sparkle. So it's essentially trivial. And the way we do this is we map every node within the query graph into a variable. This, of course, notably includes the properties. And then we can map any edge into a triple pattern, 1-for-1. So as you can imagine, the query graph we build strongly represents or is in very strong correspondence to the generated Sparkle code. And then we can enforce the set membership, i.e. the correspondence to the set of IDs that we retrieved earlier via semantic search via in. Unfortunately, graph database systems are in a pretty bad state right now. So the majority of code is actually tacked on here just to rewrite the Sparkle code we generated to SQL and then be able to execute it on a relational database system. Okay, so
SQL wins, essentially.
Yeah. Okay, so just to make this a bit more concrete, and I hope you can read this, but it's pretty difficult to fit all of the code on the slide. So here again, we have the query graph, the query we're currently constructing. And the way we translate this into Sparkle is fairly trivial. So we want to, again, retrieve movies. So we'll call this variable h0 for head of the query 0. And then we'll enforce constraints on the query. So we'll first say that m is instance of movie, right? And the way we do this is we say that the variable has to be instance of, which is this the only hard-coded predicate, which gets generated when we expand the unary predicates. And we'll say that it has to be instance of A1, and where we say that A1 has to be in this list of identifiers that we retrieved earlier. And then we just go through the list of edges in a fairly straightforward way. So we'll retrieve, or we will enforce the constraint that M was directed by D, and then we'll say, I will fix the list of directed by here, which in our case is just a single property. And then we'll go on and we say that D has to be married to A. Again, we'll use the spouse predicate we retrieved earlier, and then so on. We just continue down our list. of edges. And finally, we enforce basically that M has to have a cast member of A. Right? Yeah.
I don't know if you plan to go deeper into this, but I wanted to point out how challenging query evaluation is.
Yeah.
Because in general, every entity in every predicate can be one of a long list. So you have to join very, very big tables in order to get it.
Yeah. Yes.
And you could make one mistake because this Q12362 could have another meaning than you could think of, right? So you still need to keep in mind what the IDs are here. So
Yes, exactly. I'll get into that in just a second, how we make this presentable to the user, even though we might have more matches in general, right? This is one of the key things that we'll do in the post-processing stages, kind of present this mapping in a reasonable fashion to the user. Okay, so now we've generated the query. There's one more important fact, as you pointed out, we need to retrieve all of the intermediate mappings so we can work with them later. So we'll, in every row of the result, we'll know how it was derived. So we'll get all of the corresponding matches, i.e. basically which of these identifiers resolved to. Okay, and now we'll get into the post-processing stage. Basically at this stage, we're almost done. We're going to look at the results. So this is how they're going to be represented in the user interface. So we see at the top the natural language query that we have, which is movies where the director is married to a member of the cast. And then down below, we'll see the results retrieved by QirK. We can see that there's a confidence score associated with each result. And also, if we zoom into this bit, we'll see the exact mapping performed. In our case, we just have a single valid mapping, right? There could be multiple below, and they're grouped by essentially the mapping. But we can see here how the result was derived. So we can see that movie doesn't actually exist in the knowledge graph in the meaning that we wanted to have. And so it was mapped to film, and correspondingly director actually exists as part of the knowledge graph. So we map it to the label director, and similar we proceed with married and cast, right? So we can see exactly how the result was derived. And this way we can provide basically a data lineage of how these results were retrieved. And again, we could provide a confidence score, which we cannot really see in like ChatGPT. It will often say something that is, it will sound very confident, even though it's completely wrong, right? What we can also see is that even though we generated this IR via the LLM, only a single only a single property in the IR was valid, right? So which was the director. Everything else got mapped behind the scenes. And with this kind of mapping, we hope that the results basically remain interpretable. And you can basically view through these tabs, and we'll see this in just a second. You can step through these tabs and see individual stages of the retrieval process. And even if the results were wrong here, you'd know why they're wrong and where the mapping went wrong. And if, on the other hand, this mapping looks reasonable to you, you can be confident in the results. So, yeah. And with this, I will step to the demo and we'll try to question the scary part. Yeah. Yeah.
And the server is on which continent?
Maybe it's a bit slower because this server is currently hosted in Zurich, so it might take a bit longer. And then now yes, for some reason I
transferred, because we did a lot of post-processing on Wikidata, so we transferred the whole thing from the EW network to not to core.
So you were also involved?
Yeah. So I don't know. It might be cut off because of this. Here. Okay. So now everyone can hopefully see the screen. So this is QirK's primary interface, and we can basically ask any kind of question here in natural language. So let me just type here. I can get my mouse here. Okay. So we could, for instance, ask the question, movies where the director married to a member of the cast, right, as we had before. And then we can see it walking through the individual stages. So it just generated the intermediate representation via the knowledge graph. And then the execution, as Dan pointed out, takes some while, takes some time.
This was fast.
Yeah. Yeah, it's still 8 seconds for this query, so it's still quite a bit, right? Yeah. So here we can see the list of results, right? And these are like quite a bit of results, so this probably wouldn't have been possible via the LLM. And then we can see exactly how the mapping was performed. Again, we can see the intermediate representation. It chose to do the same mapping we did before. Apparently, that's a very canonical mapping. And then we can scroll through how basically here, of course, it's going to have slightly different names for the individual variables, but it basically will generate a similar graph as we've seen before. We can see the individual variables, the connections between them here as labeled edges. Again, all of these are actually nodes, right? And then we can look at the generated Sparkle code, which looks pretty much the same as what we've seen earlier. And then, yeah, the SQL code we generate, also looks still, I put in some time to make it look somewhat reasonable, but of course, it's not the canonical translation here.
So that gives any optimizer the in clause.
Yes, yes.
Yeah.
And this is a problem. So I thought about like if there's a single property here, we can directly inline this property, but on the other hand, that makes it look a bit less difficult. And
I think an optimizer should be smart enough
yes.
to do it, but if you have multiple, then they are
yes. Right, and we've talked about some approaches to make this a bit faster, but yeah, I don't think anyone has implemented them because it's quite a unique set. What we can also ask is maybe the question from before. I can get my mouse up here. Oh, it's quite difficult. Oh, yeah, okay. I can do it like this. Oh, yeah, yeah. Okay. Thank you. Yeah. So now we can say maybe name people who received both an Oscar for merit and a Turing Award, because I'm sure I sparked your interest into who that is. And here we can see the actual only valid result, right? And we can see how the mapping was performed. And again, this would be the stage where we could maybe have some doubts, right? If if Oscar for merit got mapped to Oscar for physics or something, right? We would immediately know, and it would just not output that result and tell us that's it. But instead, we see exactly how the result was retrieved. And again, here this mapping looks reasonable, so we're pretty confident in the result. Yeah, yes. So here we can see how this mapping gets performed. We can also step through a kind of trivial query graph we haven't seen before. See here, it's actually substantially more. And this is because like there are a bunch of entities that map to Oscar. And so we'll see them here as part of the Sparkle query. And then the SQL query, again, is just a bit inflated. Yeah, and here this works reasonably fast.
How robust is it? Like, if you rephrase the question,
Yeah.
but logically,
Yes.
like, can you say, name Turing Award winners who also received Oscar for merit? Like, would you get the same answer?
It depends. Like, it highly depends. Sometimes it's able to infer that. We can try later on with some different results, but yeah, it totally depends on the concrete query. There are like quite a couple of steps where this can go wrong. So for instance, in the IR translation, we've seen that sometimes the IR is just not as good. then oftentimes we pick a top K as part of our mapping, and this is sometimes where it will go wrong, and it just depends, right?
But how do you build intuition around the phrasing of the question to know which one this will do well on? And which one?
Ideally, you wouldn't have to, right? The way to get around this and what we thought about is just improving the way the IR gets generated. So yeah, but this maybe we can discuss at the end. We
Try that, choosing the word winner who also.
yeah. Yes, I award winners who have also won an Oscar. And, yeah.
I should emphasize the emphasis of the project was
Yeah,
not
so-
to build QirK,
yeah.
but it was QirK. So the user is supposed to write directly. in
Yes, so this is one of the things we've seen, right? So here the predicate is way too specific, right? So it will just say Turing aware winner X, which is something that we've thought about fixing, right? So you can imagine for these cases, you would find something different. But yeah, in some cases, the IR, the mapping from natural language to IR is not perfect.
What if you said, name movies where a cast member is married to the director? Like, would that be an easier one?
We can try it.
So
I'm just trying to
also,
build an
if we
intuition.
wanted to kind of, if you wanted to wrap up,
Yeah.
stop recording,
Oh,
take
yeah.
questions.
Yeah.
you can also do it.
Yeah, we can try all of this later on. Yeah, yes. We can also try, of course, some of the queries we've seen before with aggregation, but yeah, or just
Show the movies from Schwarzenegger.
sorry.
Show movies from Schwarzenegger.
Yeah, I like. I think one of the first ones we tried, and I think like mine was mouse, which was a favorite of Anton, which was movies directed by Anton Lykov. So this is also like I think this was Anton's favorite query. This is why it's all over the docs, and then we see this actually works well. And here we also have a fairly specific QirK IR predicate. So it says directed movie, right? Which isn't part of the autograph, right? So it depends really on how well the mapping performs, and sometimes the mapping doesn't work well. Yeah.
To generate the mapping, maybe I missed it. Do you do fine tuning or like
Yeah.
zero shot like prompt engineering?
We do zero-shot prompt engineering, but the idea we want to integrate here is to have a database of natural language questions to IR mappings that we can basically perform RAG on before performing the mapping. And this, I think, will substantially help with these kind of things. So it has a chance of seeing how, yeah, that you don't have to be too specific, right, with the IR translation. Yeah. Yeah. Yes. No, yeah. Yeah, okay. So let's wrap up the demo. So just to summarize what we've seen before, this is QirK, our way of answering questions via intermediate representational knowledge graphs. Our approach was basically to take natural language questions, translate them into an intermediate representation using an LLM, and then we'll later on ground this intermediate representation using similarity search and resolve semantic ambiguity using the knowledge graph directly. And yeah, in this way, we hope to eventually, after we've overcome some of the initial difficulties, provide the best of both worlds, right? We want accurate and complete results combined with the user friendliness of traditional LLMs, right? And where to go from here, we already mentioned this before, but we want to integrate some kind of RAG generation to help the LLM generate better IR. And then we could look into what I think was also discussed before, some entity linking, but I think especially on Wikidata, there are some scalability concerns there. And then, yeah, we definitely need to kind of incorporate some improvements here, because for more complicated queries, it does tend to, the execution time is pretty high. And there are some ideas to get around this. And I think it would be quite interesting to explore how they apply here.
I should mention Kuzu is the project by Ilias Fountalis from the University of Waterloo.
So I know for certain they have integrated worst case optimal joins, which are not present in Postgres, which we're running this on. So this is one of the downsides.
Okay.
Yeah.
Okay. Okay, so it's time to stop the recording, and now we can take questions for Luca.